So what is a ROC curve, and what does it do, and what does it tell us? A ROC curve is short for Receiver Operating Characteristics Curve. It was derived out of World War II, and in this picture we see a picture of a Royal Air Force radar operator looking for German planes coming over to bomb England, coming over the English Channel. So it was very important for them to be right. If they saw a blip on the radar that they thought was a bomber, then what they would do is they would scramble the fighters, and it was very expensive to launch all the planes and the pilots and get people up there. But if they missed it, then that was expensive too. And so there needed to be a way to see how well the radars were doing. When those blips showed up on the screen, how confident could we be, and how often were we right that it really was a plane, or did we sometimes find out that it was a flock of geese or something like that? If you look at a radar screen, you can see that sometimes it's not always easy to be able to identify what's really a blip that we should maybe take seriously and what's a cloud formation or something else. And so they developed the ROC curve. The idea with the ROC curve is that we would chart the items that we thought were the planes, that were the things that we were looking for, planes in this case, and then you could sort them from the ones that you thought were the most likely to be planes to the ones that you were thinking were still planes, but you didn't have as much evidence. Maybe the blip was not quite as dark on the radar. And so up here we have sorted the most blips most likely to be planes, all the way down to things that we still think are probably planes, but maybe the blip isn't quite as dark. So, and of course, this has been generalized now to use for predicting all sorts of things, predicting, who will win a game, or who will buy one of our products, or who will get sick, or whatever. Now, the way a ROC curve is laid out is you have true positives, or the true positive rate or proportion, on the vertical axis, and you have the false positive rate or proportion that is along the horizontal axis. The idea here is that as a prediction comes in, these were all predicted to be positives. As a prediction comes in, if we are right, so this first prediction was actually, let's say, a plane in this case, and so we found that it really was a plane. It was predicted to be a plane, and so good. So we went up. So 1/10 of all of our predictions that were true, that were ones in this case, we went up 1/10 the distance. Now, if you count these, we have 10 ones and 10 zeros. And I set it up this way for the simple example. So if first thing we do is we identify one, and that's a true positive, good. Then we identify several more. So for each one of those, we go up 1/10 the distance, okay? And then, even though we thought this blip was a plane, it wasn't. It was a false positive. And so now we've got 1/10 of the false positives. So we move to the right 1/10 of the distance on that axis. Then it was followed by two true positives, and so we go up 1/10 and 1/10 the distance. And then we hit another false positive, and so now we move over here. There's our second false positive. So now we've used up 2 out of the 10, or 20% of our false positives. And then we have 2 more true positives. Then we hit a series of 5 false positives, and then 2 more true positives. And then all that's really left are false positives. So basically what's happening here is we're getting a visual representation of our rightness and our wrongness. The true positives versus the false positives are all laid out on this grid. And the further we can get up to the upper left, the better our radar is doing. Now, with a perfect radar, we would find all of the true positives and never get one false positive. So we would march up until we found 100% of the true positives before we ever had a false positive. That would be a perfect classifier. Generally speaking, we're usually not perfect. We're usually not perfect when it comes to something like this. False positives tend to be in our results, and the order actually matters. If you get a true positives before you can get false positives, your receiver, your characteristic chart, is going to be showing better than if you don't. Let's look at another example or two. In this case, we have on the orange, we have an orange classifier and a green classifier. And you can see down here that as we move up on the vertical axis, we had 8 out of 10 or 80% of our true positives, and then we had 20% of our false positives. And so that means that there are 4 of those boxes, they're not within the curve, and so we have an area under the curve of 0.96. Then if you look at the green classifier, the first thing it did, the first 2 predictions it made, it was wrong. It thought they were true positives, but they were false positives. And so it moved to the right 2 positions, and then it found all of the true positives, and then all of the rest of the false positives. Now, if you look at this example, you can see there's a big difference in the area under the curve. The orange classifier has got a 0.96, and the green classifier has a 0.8. So that's actually a classifier would be 0.8. And so you can see that there's a big difference between 0.96 and 0.8 in terms of what's under the curve. Now let's look at an example where the curves are not so blocky. So we still have from 0 to 100% and from 0 up to 100% over here. But basically what's happening is we have more gradual curves. What's happening is the reason why these were so blocky was because each time we had a correct or a mistake, it moved us 10%. Usually that doesn't happen. Often we'll have thousands of predictions to be evaluated. And so we might have just a very small increment moving up or a very small increment moving right. So for example, if we had 1,000 true positives, then each time we find one, we would move up 1/1000th of the distance from the bottom to the top. Same thing with the horizontal axis. And so we get more gradual curves. Now in this particular example, we have what I would call an early curve and a late curve. In this case, we're doing better at getting true positives early on, and then we actually start doing worse than equaling true positives and false positives. So the area under the curve for the purple classifier, the early classifier, is really 0.5. There's just as much below the curve back here as there is above the curve here. Well, the late classifier is worse because we're getting more false positives early on, and then it starts improving and starts doing better. And yet, because it has some area that's down below the equal finding true and false positives and some that's above, then it's going to be equal to, essentially it's going to be 0.5. So when you look at these, which one's better? Well, the one that finds more true positives early on is better. And so even though they both would have essentially the same area under the curve, this is more valuable to be able to have these where we're doing a better job of finding the true positives and the false positives.